Hello, and welcome to my first video here on momentum. So, to start off, it might be useful to give you the momentum equation. So, the momentum of a moving object is equal to its mass, the mass of that object, multiplied by the velocity of the object. We represent momentum by a lowercase p, m and v for mass and velocity. And here are the units. We are going to look at collisions first in terms of where to apply this momentum. Consider this. Before a collision, only a little cart M was in motion. There was a stationary other cart with the same mass. After the collision, the two carts stick together. Imagine them being connected by Velcro. The velocity halves. If you take a look at the car comes in at a high velocity and that velocity goes down as it collides with the other car, and both of them move off at about half the speed of the original car. If we consider this in terms of what mass is in motion at the time, so before the collision, only the little cart was moving. So before the collision we had mass 1 moving, and after the collision we had double the mass, half the velocity. Take a look again. Came in quickly. They both move off together slowly. Okay, a second example. This time without the same amount of mass in each cart. So before the collision, again we've only got one of the carts moving. That's a small cart moving towards something that's double its mass. Again, we set the velocity to 1. After the collision, imagine them both stuck together, the velocity will then reduce down to a third of its original velocity. Let's take a look at how that might look in an animation. So that's coming in, and then that just goes off at a third of its initial velocity. So, again, looking at the masses. So the masses that were in motion, before, we only had mass m, but afterwards we had 3m. The two carts effectively acting like one large cart. Here it is again. Reduces to about a third of the speed. Okay, so let's consider just what happened after the collisions. Okay, so I'll take a look at what happens if the mass increases, by how much, and what happens to the velocity. So in the first example, we had doubling the mass, which led to halving of the velocity. In example 2, we tripled the mass, which divided the velocity by 3. You notice, therefore, that the momentum is conserved. This leads us on to one of your main conservation laws in GCSE physics. This one is the law of conservation of momentum, and it goes as follows, or the formal definition is as follows. In a closed system, the total momentum before an event is equal to the total momentum after the event. Okay? In other words, closed, by the way, that just means that there are no external forces acting. And to summarise, total momentum before is equal to the total momentum after, or the momentum before equals momentum after in equation form. So we've had a look at collisions. Let's take a look at the other version of problem that you might come across. Collisions involve one of the masses or some kind of mass moving in the first place. The second kind of problem involves the momentum starting off as 0, and that is an explosion problem. So in explosion problems, we have an initial velocity which is set to 0. So let's write that down. Initial velocity is set to 0. And because momentum is equal to mass times velocity, then the momentum has to be 0. So in order to conserve this momentum, the momentum going in one direction has to equal the momentum going in the opposite direction so that they cancel out. So consider two carts of the same mass involved in an explosion. If they're the same mass, then they have to move away with the same velocity. However, most situations aren't that simple. So if we take a look at a situation where we have two carts moving away, one with double the mass of the first cart, then because the masses aren't equal, then the velocities can't be equal either. But we know that the momentum is conserved. So how do we solve this? Well, if on the left-hand side we have m times v, then on the right-hand side we have 2m times half v. Think back to the original collision problem. So increasing, doubling is going to lead to halving your velocity. Doubling the mass halves the velocity. But have we forgotten something? Well, p can't equal p, can it? Because if we add two positive numbers together, we'll end up with a positive number. So we have to, in order to get back down to p equals 0, have a negative number. And for that, we need to remember that momentum is a vector. So, in other words, it has a size and, of course, it has a direction. So you cannot completely describe a momentum without giving the direction that the momentum is acting in. So if we take a look at the directions of the momentum, so p going that way is equal to p going that way, but with a negative sign. So p plus p is equal to 0. So to do this, the velocity will have to be positive in one direction and negative in the other. And that is because velocity is another vector. In practice, what we tend to do when we're solving problems is that we tend to have something like this. So the mass of object A multiplied by the velocity of object A plus the mass of B multiplied by the velocity of B is equal to 0. Or, a better way to remember it is this way. So if you have mass of A multiplied by the velocity of A, similar to before, is equal to negative mass of B multiplied by the velocity of B. And this is your key equation for momentum. Let's apply that to a problem. So the problem is a explosion problem, and it is a classic question. It's about gun recoil. A Brigadier pistol weighing 1.9 kilograms fires a 17-gram bullet at 370 meters per second. What is the recoil speed of the gun? So, first off, we divide our page in our minds. We don't have to do it physically, into two halves. On the left-hand side, we'll put down the numbers for the gun, and on the right-hand side, we'll put down the known numbers for the bullet. So the gun has a mass of 1.9 kilos. We don't know the velocity. The bullet is 0.017 kilos, and the velocity is 370 meters per second. We know that the momenta on both sides will balance. Filling in or substituting gives us this value, and we calculate the remainder like this, giving us a recoil speed of 3.3 meters per second. And this is where the numbers all came from, in case you missed it the first time. It's also prudent to take a look at where the mark scheme would award you some points. So you get a point for that, you get a point for the substitution, a point for the right number, and a point for the unit. And there's a Magnum 45 hitting someone in the face with a recoil speed of about 3.3 meters per second. Thank you very much for listening.